Hello, friend. Tonight, we're going to drift into the quiet story of Dmitri Mendeleev, the scientist who found hidden order in matter itself. So get comfortable, let the day fall away, and let's slowly fall asleep to science. Chapter 1. The World Before the Periodic Table. Before the periodic table existed, chemistry was not yet a single clear map of matter. It was a growing collection of substances, reactions, names, weights, and practical habits gathered from mines, furnaces, pharmacies, laboratories, and workshops. Chemists could isolate gases, burn metals, dissolve salts, and create compounds with increasing skill. But the deeper order behind those transformations remained difficult to see. The modern idea of an element as a substance that cannot be broken down by ordinary chemical means had begun to take shape in the late 18th century, especially through the work of Antoine Lavoisier, who tried to classify known substances in a more systematic way. Yet even Lavoisier's list still reflected a world in transition, because chemistry was only beginning to separate true elements from older ideas about heat, air, and material principles. That earlier world had inherited many layers of thought. Ancient traditions spoke of a few basic elements such as earth, air, fire, and water, but those were philosophical categories rather than experimentally defined substances. Early modern chemistry then passed through the age of alchemy, where practical discoveries about materials often existed beside symbolic interpretations of nature. By the time chemistry became more quantitative, experiment began replacing speculation. Careful measurement of mass, better control of reactions, and clearer naming of substances made it possible to ask a sharper question. What are the fundamental kinds of matter that do not decompose further in ordinary chemical change? In the early 19th century, that question was still surrounded by uncertainty, because chemists did not yet have a stable framework for atoms, molecules, or even the correct formulas of many familiar compounds. One of the great steps toward clarity came from John Dalton. Dalton argued that matter is composed of atoms and that atoms of different elements differ in mass. Some parts of his theory were incomplete or later corrected, but one feature was transformative. If each element had its own kind of atom, then matter was built from distinct units. This made it meaningful to compare substances by relative atomic weight and to think about compounds as combinations of atoms in fixed proportions. Even so, this new atomic picture did not solve everything. Chemists still disagreed about how to assign atomic weights and how to distinguish an atom from a molecule. The language of chemistry had become more precise, but it was not yet fully settled. This uncertainty mattered deeply. Without reliable atomic weights, it was difficult to compare one element with another in any rigorous way. A chemist might know that sulfur formed acidic oxides, that sodium was reactive and metallic, or that chlorine combined readily with metals and hydrogen, but turning those observations into a universal order was another matter. If the weights were wrong, the comparisons were distorted. If formulas were wrong, families of elements looked less like families and more like coincidence. For much of the first half of the 19th century, chemistry possessed a growing store of facts without a universally trusted method for arranging them. It was rich in knowledge, but poor in architecture. And yet patterns kept appearing. Chemists began to notice that certain elements behaved like one another. Lithium, sodium, and potassium shared obvious similarities. Chlorine, bromine, and iodine formed another recognizable family. Calcium, strontium, and barium also seemed related. Johann Dobereiner drew attention to such groups, later called triads. In some of these sets, the properties of the middle member appeared to fall between the other two, and even the atomic weights hinted at a numerical relationship. These triads were not a full system, and they covered only a limited number of known elements, but they mattered because they suggested that the elements were not isolated facts. They might belong to a larger natural order waiting to be uncovered. Each new element widened human knowledge, but each discovery also made the disorder more obvious. By the middle of the 19th century, dozens of elements were known. Some had been isolated from minerals, some from ores, some from gases, some from painstaking work in analytical laboratories. The problem was no longer merely discovering substances. The problem was understanding how they belonged together. Chemistry had reached the point where curiosity demanded structure. Several thinkers tried to provide that structure before Mendeleev. Alexandre-Émile Baguier de Chamcourtois arranged elements by atomic weight on a spiral wrapped around a cylinder and observed that similar properties recurred at regular intervals. John Newlands later proposed his law of octaves, noting that when the known elements were arranged by increasing atomic weight, chemical similarities seemed to repeat with a rhythm reminiscent of music. These were bold insights. They brought chemists closer to the idea of periodicity, the repeating pattern in elemental behavior. But they were not yet convincing enough to settle the matter for the broader scientific community. Some schemes were too awkward, some depended on imperfect data, and some forced the known elements into patterns that did not quite fit. Newlands, in particular, saw something important, even if his formulation was not fully accepted at the time. He recognized that recurrence was not random. Similar chemical properties reappeared after intervals when the elements were ordered by weight. But his table left no room for undiscovered elements, and the known chemical world still contained irregularities that resisted a simple musical analogy. The scientific community reacted with skepticism. Before a grand pattern becomes obvious, it usually appears first in fragments. Another obstacle was the confusion surrounding atomic and molecular formulas. The same substance could be described in different ways by different chemists, depending on which atomic assumptions they used. This is why the Karlsruhe Congress became so important. Chemists gathered there in the early 1860s to discuss the foundations of their science, including atomic weights and chemical formulas. The meeting itself did not instantly resolve every dispute, but Stanislaw Cannizzaro's clear use of Avogadro's ideas helped many chemists see a more consistent route through the confusion. His work on atomic weights proved especially influential for later classifiers of the elements. Both Mendeleev and Julius Lothar Meyer were shaped by this emerging clarity. This moment is essential. The periodic table did not appear out of nowhere as a stroke of isolated genius. It emerged from a long struggle to make chemical language coherent. Before the table could reveal order, chemists had to agree, more or less, on what they were comparing. They needed dependable weights, defensible formulas, and enough experimental evidence to tell resemblance from accident. In that sense, the world before the periodic table was not merely chaotic. It was a world in the act of becoming measurable. The order was already there in nature, but the human tools required to detect it were still being sharpened. There was also a philosophical tension running through 19th century chemistry. Were the elements simply a list, destined to grow forever without deeper logic, or were they expressions of a hidden system? If they formed a system, what kind of system was it? Was it based on weight, on combining power, on reactivity, on physical properties, or on some still unknown principle? Chemists could see resemblances, but they did not yet know which resemblances mattered most. To classify well is to say that the world itself has joints, and that human thought has begun to find them. Before Mendeleev, chemistry was standing at that threshold. It is also worth remembering how material this search was. The elements were not abstract tokens on paper. They came from flames that changed color, crystals that formed slowly from solution, metals that tarnished, gases that suffocated or burned, and residues left after repeated purification. New elements were teased out of stubborn ores and separated by difficult procedures. Their identities were inferred from repeated patterns in reaction and composition. Every improvement in analysis made the hidden population of matter more visible. And as that population grew, so did the pressure to find a natural arrangement capable of holding it all. Without such an arrangement, chemistry risked drowning in its own success. So the world before the periodic table was not a blank space waiting for one man to write upon it. It was a crowded and restless intellectual landscape. Lavoisier had clarified the idea of an element through careful chemical analysis. Dalton had given chemists a way to think about distinct atoms with distinct masses. Dobereiner had shown that some elements gathered into families. De Chancourtois and Newlands had glimpsed repetition. Cannizzaro had helped stabilize the language of atomic weights. Piece by piece, chemistry was approaching a revelation. The facts were accumulating, the confusion was narrowing, and the hidden rhythm of matter was beginning to press against the edges of scientific thought. This is what made the period just before Mendeleev so extraordinary. The science was full of fragments that did not yet know they belonged to one another. Different chemists had touched different parts of the same truth, but the overall picture was still waiting. The elements existed, their properties existed, their relationships existed, but the full form of their order had not yet been drawn into view. And that is where this story becomes quietly beautiful. Nature did not suddenly become orderly when the periodic table was made. Nature had been orderly all along. What changed was human sight. The chemists of the early 19th century were feeling their way through fog, carrying balances, notebooks, glassware, and ideas that were not yet complete. Slowly, patiently, they learned how to compare what had once seemed incomparable. They learned how to trust measurement more than impression, and structure more than habit. In time, the scattered pieces would align. For now, it is enough to rest in that unfinished world, where knowledge was growing, but the final pattern had not yet appeared. There is something calming in that slow approach to clarity, a reminder that confusion is sometimes only the early stage of understanding. Let the mind loosen its grip for a moment, and let the quiet order of the material world hold the rest. Chapter 2. Who Mendeleev Was. Dmitri Ivanovich Mendeleev was not simply a chemist who arranged the elements into a memorable pattern. He was a scientist formed by hardship, discipline, restless curiosity, and an unusually broad way of thinking about nature. To understand why he mattered, it helps to see him not as a man who stumbled upon a clever table, but as a mind trained to search for order across many kinds of physical reality. He worked on chemistry, certainly, but also on gases, liquids, solutions, measurement, education, industry, and the foundations of scientific classification. What set him apart was not only intelligence, it was a particular habit of thought. He wanted scattered facts to belong to a coherent system. He was born in Tobolsk in Siberia in the early 19th century, far from the great scientific centers of Western Europe. His father was a teacher, and his mother came from a family connected with glass production. The circumstances of his childhood were difficult. His father lost his sight around the time Dmitri was born, and later died while Dmitri was still young. His mother then took on the burden of supporting a large family. She helped run a glass factory owned by her relatives, and for a time that factory became the practical basis of the family's survival. When it burned down, the family's fragile security was broken again. This sequence of loss is important not because it turns Mendeleev into a legend of suffering, but because it helps explain the seriousness that marked his later life. He grew up in conditions where knowledge was not decorative. Education was a route through instability. His mother seems to have played a decisive role in that route. After the destruction of the factory, she took him westward so that he could continue his education in St. Petersburg. That journey from the edge of Siberia toward one of the intellectual capitals of the Russian Empire has often been remembered with almost symbolic force. But behind the symbolism was something concrete, a family making a difficult wager on learning. Soon after helping him reach that next stage, his mother died. By then, however, the direction of his life had been set. He entered the main pedagogical institute in St. Petersburg, where he was trained not only in chemistry, but in the disciplined culture of scientific study and teaching. This mattered. Mendeleev did not emerge from a narrow technical background. He was educated in a setting that expected future teachers and scholars to think systematically and communicate clearly. From the beginning, one of his strengths was that he could connect research with explanation. He was not merely a collector of results. He was someone who wanted knowledge to be organized, taught, and made intellectually durable. Later, when he wrote major textbooks and developed broad chemical arguments, this educational background would become one of his hidden advantages. His early adult years also show something essential about his character. After graduating, he briefly taught in the south of the empire, in places such as Simferopol and Odessa, before returning to St. Petersburg to continue academic work. He earned an advanced degree and began research in organic chemistry. That alone would have made him a respectable chemist of his time. But he did not remain confined within one specialty. Supported by a government fellowship, he then traveled to Heidelberg, one of the important scientific centers of Europe. There he encountered a more international scientific world and came into indirect contact with major figures of chemistry. Yet even in Heidelberg, Mendeleev showed an independence that would remain characteristic of him. Rather than attach himself comfortably to one established laboratory hierarchy, he set up a laboratory in his own apartment. This detail is revealing. It suggests self-reliance, but also a certain stubbornness. He was willing to work near great authorities without fully dissolving into their schools. He learned from the wider chemical world, but he preserved his own line of inquiry. In science, that balance is rare. Some researchers become isolated and miss what others know. Others become so shaped by existing institutions that they stop seeing beyond them. Mendeleev absorbed the best available methods and debates, but he kept the confidence to think independently. One of the important scientific influences on his generation was the growing clarification of atomic weights and formulas. The chemical world of the mid-19th century still contained ambiguities, but it was becoming more exact. Mendeleev followed these developments closely, including the ideas that spread after the Karlsruhe Congress, where debates about atomic weights and molecular formulas were brought into sharper focus. He was not only a man of intuition. He was a man who watched the technical foundations of chemistry carefully. This combination would later prove crucial. A large pattern can only be trusted when the measurements underneath it are treated seriously. When he returned to Russia, he did not settle into a quiet life of narrow laboratory routine. He became a professor, first of chemical technology, and then of general chemistry at St. Petersburg. Teaching was not a side activity for him. It was one of the places where his science matured. In trying to present chemistry as a connected body of knowledge, he faced a problem more demanding than mere research specialization. He had to decide how the known facts of chemistry should be ordered so that students could understand them. This pressure toward coherent exposition shaped his thinking deeply. His great textbook, Principles of Chemistry, was not just a repository of information. It was part of the intellectual environment in which his most famous insight emerged. This is one of the reasons it is misleading to imagine Mendeleev as a pure visionary detached from practical science. He was intensely practical in method. He wanted categories that worked, explanations that held together, and measurements that could support general conclusions. He studied substances not as isolated curiosities, but as members of a wider natural order. In his chemical work before and after the periodic law, he also investigated gases and liquids, asking how physical properties changed across conditions. He worked on thermal expansion, the behavior of solutions, and the deviations of real gases from idealized expectations. Some of his specific ideas did not survive unchanged, as often happens in science. But the broad style of his work remained consistent. He looked for relations between measurable properties, and he preferred broad frameworks over disconnected facts. That style extended beyond chemistry in the narrow sense. Mendeleev later became involved in matters of standards, industry, and metrology, the science of measurement. This is entirely fitting. A man who sought order in the elements also cared about precision in the practical world. He was interested in petroleum, technology, and the scientific infrastructure needed by a modern state. In him, theory and application were not enemies. The same mind that cared about periodicity could also care about weights, measures, and industrial processes. He belonged to an age when science was becoming both more abstract and more materially transformative, and he moved with unusual ease across that divide. Personality also mattered. Accounts of Mendeleev often describe him as forceful, confident, and sometimes difficult. He could be combative in debate and resistant to views he rejected. He was not a quiet bureaucrat of knowledge. He had the temperament of someone who believed strongly in the explanatory power of his ideas. That kind of temperament can become a weakness when it hardens into dogma, and Mendeleev was not free from that risk. He defended some views that later science would leave behind, and he did not welcome every new development with equal flexibility. But his firmness also gave him the courage to defend a bold ordering of the elements when the evidence was still incomplete. Scientific revolutions often require not only insight, but also the resolve to trust a pattern before the wider community fully accepts it. There is also a philosophical side to him that deserves attention. Mendeleev cared about what elements were, not only about how they reacted. He did not treat chemistry as a bag of recipes. He wanted to understand the status of elements as basic constituents of matter. In that sense, he stood at a threshold between older natural philosophy and modern physical science. He lived before the electron, before the proton, before the neutron, before quantum theory explained periodic behavior in terms of electron structure and atomic number. So his world did not yet possess the deeper microscopic account that later generations would take for granted. But he still sensed that the elements formed a lawful system rather than a random inventory. That confidence in hidden order is part of what made him great. It is tempting to compress such a person into a single image, the bearded Russian sage arranging chemical cards until the pattern appears. But that image, while memorable, is too small. Mendeleev was formed by geography, family hardship, disciplined education, international scientific exchange, pedagogical labor, broad physical research, and a persistent urge to classify the world without reducing its richness. He was both provincial and cosmopolitan, both practical and theoretical, both teacher and investigator. He came from the outer reaches of empire and entered the center of science, carrying with him an unusual mixture of endurance and ambition. He also belonged to a century in which chemistry was changing from an expanding craft of substances into a science seeking deep structure. That historical moment met a person unusually suited to it. A different chemist might have seen only a set of useful comparisons. Mendeleev wanted a governing law. A different teacher might have been satisfied to arrange facts for convenience. Mendeleev wanted their arrangement to reflect nature itself. A different researcher might have remained within one technical problem. Mendeleev ranged across many. This breadth did not distract him from his central discovery. It prepared him for it. There is something scientifically important in that preparation. Great discoveries are often described afterward as sudden flashes, but they are more often the visible crest of long mental habits. Mendeleev's habits were already tuned toward comparison, synthesis, and structural reasoning. He had spent years moving between measurement and theory, between teaching and research, between particular substances and general relations. By the time the periodic system came into view, he was ready not only to notice a pattern, but to recognize that the pattern deserved to be trusted. So who Mendeleev was cannot be separated from what he found. He was a chemist, but also an organizer of knowledge. He was a professor, but also a builder of conceptual frameworks. He was a researcher of matter, but also a defender of intelligibility itself, of the idea that the material world is not merely a crowd of facts, but something capable of lawful arrangement. That conviction may sound ordinary now because the periodic table is so familiar that it feels inevitable. In his own time, it was not inevitable. It required someone whose life had trained him to believe that beneath confusion, there may be a structure patient enough to wait for recognition. And perhaps that is one of the quiet lessons in his story. A human life is brief, local, and often burdened by accident. Yet a human mind can still touch patterns older than nations and deeper than memory. Mendeleev did not invent the order of matter. He simply lived long enough and thought clearly enough to glimpse it. In that way, his life reminds us that even in a passing world, the mind can sometimes meet something enduring. Chapter 3. The Problem of the Elements. By the time Dmitri Mendeleev began thinking seriously about how the elements might be arranged, chemistry had already become a rich and successful science. It could identify substances, separate compounds, analyze composition, and describe many reactions with growing precision. But beneath that success lay a difficult and unresolved problem. Chemists knew many elements, yet they did not fully understand how those elements were related to one another. The science possessed an expanding population of basic substances, but no universally satisfying way to organize them. This was not a minor inconvenience. It was a structural weakness at the center of chemistry. An element, in the chemical sense, emerging through the late 18th and 19th centuries, was understood as a substance that could not be decomposed into simpler substances by ordinary chemical methods. That definition gave chemists a working foundation, but it did not tell them how the elements themselves should be understood as a set. Oxygen was an element, iron was an element, chlorine was an element, sulfur was an element, copper was an element, and so on. But what exactly did that mean beyond the fact that each represented a distinct kind of matter in chemical transformation? Were the elements simply a growing list, like entries in a catalog, or were they members of a deeper natural order? That question became harder to ignore as the number of known elements continued to grow. The difficulty was not merely one of quantity. It was one of relationship. Chemists could see that some elements behaved in comparable ways. Certain metals formed similar compounds. Certain nonmetals showed related reactivity. Some substances replaced others in reactions with a kind of family resemblance. Yet resemblance alone was not enough. Nature often produces superficial similarities, and chemistry needed something stronger than impression. It needed a framework that could explain why similarities existed, how far they extended, and where one family of behavior ended and another began. This mattered because chemistry was, by its nature, comparative. To understand one element well, a chemist had to compare it with others. Atomic weight, combining capacity, physical state, metallic character, density, oxide formation, acid behavior, and many other properties all seemed relevant. But which of these properties should guide classification? A system built mainly on one feature might clash with a system built on another. An arrangement that seemed sensible for a handful of substances might break down when more were included. Chemistry was trying to see a pattern while still arguing about what counted as the right clues. One reason the problem was so difficult is that the concept of the atom itself, though increasingly powerful, did not yet have the later clarity provided by modern physics. Chemists spoke of atoms and atomic weights, but they could not see atoms directly, and they did not know about protons, electrons, or the nuclear structure that would later explain the periodic table in deeper terms. Atomic weight served as one of the best available guides, but even that guide depended on correct formulas and careful measurements. If the accepted formula for a compound was wrong, then the inferred atomic weight of one of its constituent elements could also be wrong. Classification, therefore, depended not only on insight, but on the reliability of the entire chemical language being used. This made the problem of the elements partly empirical and partly conceptual. On the empirical side, chemists needed accurate analyses of compounds and dependable measurements of mass relations. On the conceptual side, they needed confidence that the categories they used truly reflected nature. It is one thing to observe that sodium and potassium react with water in related ways. It is another to decide that this similarity is part of a general law rather than a local coincidence. The move from observation to system is one of the most delicate moves in science. The sheer diversity of the elements intensified that challenge. Some were lustrous, malleable metals, some were brittle solids, some were colored gases, some were chemically violent, others comparatively inert. Some appeared often in familiar materials of daily life, while others were isolated only through specialized work in mineral analysis. Their compounds varied enormously in stability, solubility, acidity, color, and reactivity. The known chemical world looked both crowded and uneven. There were obvious clusters of resemblance, but there were also abrupt contrasts and puzzling exceptions. At the same time, chemistry was becoming increasingly quantitative. This was one of its great strengths, but it also sharpened the classification problem. Once atomic weights and fixed composition entered the picture, vague descriptions were no longer enough. If the elements belonged to an order, that order had to be compatible with measurable relations. It could not remain merely verbal or philosophical. The question became whether numerical properties, especially atomic weights, could reveal a hidden architecture beneath chemical behavior. Several early attempts suggested that they might. Certain small groups of elements displayed patterns that seemed too strong to ignore. In some cases, the middle member of a chemically similar trio had an atomic weight roughly intermediate between the other two. In other cases, a repeating rhythm seemed to emerge when elements were listed by increasing weight. These hints were important, but they did not yet solve the central difficulty. Partial patterns are not the same as a complete system. They can encourage discovery, but they can also mislead if treated too rigidly. Another part of the problem came from incompleteness. Chemists did not yet know all the naturally occurring elements. This meant that any arrangement built only from the known set was vulnerable to distortion. Imagine trying to understand a melody while several notes are missing. Some relations would still be audible, but others would seem awkward or broken. Before the periodic table, chemistry was in something like that situation. The order of the elements, if it existed, was being inferred from an incomplete sample of nature. This made every system provisional. A classification might fail not because the idea of order was wrong, but because the available evidence was still fragmentary. That incompleteness also created a psychological difficulty. Most scientists are understandably cautious about leaving deliberate gaps in a classification. It can feel safer to arrange only what is known than to make room for what has not yet been observed. But if the known elements formed only part of a larger system, then a table with no gaps might actually be less truthful than one with carefully chosen absences. Before Mendeleev, that way of thinking had not yet fully taken hold. The problem of the elements was therefore not only a problem of data. It was a problem of scientific courage and judgment. A further complication lay in the fact that different chemical properties did not all change in the same simple way from one element to the next. Metallic character might increase across one region and fade across another. The formulas of oxides and hydrides revealed certain regularities, but not always in a perfectly smooth progression. Some elements could form more than one kind of compound, displaying more than one combining pattern depending on the circumstances. This richness made chemistry real and powerful, but it also frustrated any attempt at easy classification. Nature was offering order, but not a childish order. It was structured yet subtle. The known elements also raised a philosophical question about individuality and law. Each element had its own character. Sulfur was not phosphorus, and chlorine was not bromine, even when they resembled one another. So the challenge was not to erase individuality in favor of a crude scheme. The challenge was to understand how distinct identities could belong to a larger pattern without being reduced to sameness. This is one of the deepest scientific problems in any field. How can the world contain genuine variety and still obey intelligible law? In chemistry, the elements presented that question in a particularly concrete form. Practical chemistry had strong reasons to want an answer. Without a sound classification, teaching became harder, memory became heavier, and prediction remained weak. A science that depends only on remembering isolated facts grows cumbersome. A science that discovers lawful relationships becomes lighter, more powerful, and more fertile. If chemists could place the elements into a natural system, then unknown properties might become inferable from known relations. Classification would cease to be an act of filing and become an instrument of discovery. That possibility was especially important because chemistry was not satisfied merely with naming what already existed. It aimed to understand compounds, reactions, and transformations in a general way. If the elements were the fundamental chemical actors, then a disordered view of the elements would limit the whole science. Every theory of combination, substitution, valence, and compound formation depended in some way on how the basic substances themselves were understood. The problem of the elements was therefore not a side issue at the margins of chemistry. It was close to the center. What makes this historical moment so interesting is that chemists were surrounded by evidence of order without yet possessing the final key to that order. Repetition had been glimpsed, but not yet disciplined into a universally convincing law. Similarity had been recognized, but not fully integrated with weight and valence. The known elements had become too many for intuition alone, yet the science had not fully crossed into a stable system. It was a time when chemistry was pressing against the limits of description and asking for architecture. Seen from the modern world, where the periodic table hangs in classrooms as if it had always existed, it is easy to underestimate the depth of this problem. The table now feels obvious because later science explained why periodicity occurs. Atomic number, electron arrangement, and quantum structure gave the deeper account that 19th century chemistry lacked. But before those developments, the existence of a lawful repeating order among the elements was not something that could simply be assumed. It had to be inferred from stubborn and imperfect evidence. The chemists confronting this challenge were trying to hear the grammar of matter before they knew the alphabet of the atom in its modern form. So the problem of the elements was, in the fullest sense, a problem of hidden order. Chemistry had reached a stage where facts alone were no longer enough. It needed a pattern strong enough to unify diversity, flexible enough to accommodate exceptions, and bold enough to make predictions. It needed a system that would not merely sort the known substances, but reveal that their differences and similarities belong to a deeper regularity in nature. That is why this problem deserves to be remembered as one of the great intellectual pressures in the history of science. It was not only about substances in bottles or symbols on paper. It was about whether the material world, in all its variety, could be grasped as a lawful whole. The answer would eventually be yes, but at this stage the yes had not yet arrived in full. Chemistry stood before a scattered landscape of elemental identities, aware that meaning was present, but not yet fully seen. And perhaps that is why this chapter still speaks quietly to us. The world often reaches us first as fragments, scattered facts, unfinished patterns, and separate names. Only later, if we are patient, does a deeper order begin to emerge. For a brief life moving through a vast universe, there is something strangely comforting in that. The hidden structure may exist long before we are able to recognize it, waiting with calm indifference for the mind that is ready to see. Chapter 4. The Birth of the Table. The birth of the periodic table was not the appearance of a decorative chart. It was the moment when chemistry began to recognize that the elements were not merely a collection of separate substances but parts of a repeating natural order. When Dmitri Mendeleev brought that order into visible form, he did not simply arrange familiar facts more neatly. He transformed chemistry from a science burdened by accumulation into a science capable of deeper prediction. The importance of that moment lies not only in the table itself, but in the way it changed what chemists believed matter could reveal about itself. By the late 1860s, the known elements had reached a critical mass. There were enough of them for patterns to become visible, but not so many that the full structure was obvious at a glance. Mendeleev was working at that exact threshold. He was preparing material for his chemistry textbook and needed a way to present the elements in a coherent sequence. This practical pressure mattered. The periodic table did not begin as an abstract philosophical game. It emerged from the scientific need to make chemical knowledge intelligible. In trying to teach chemistry as a system, rather than as a heap of isolated facts, Mendeleev placed himself in the path of one of the most powerful patterns in science. He worked with the best data then available, especially atomic weights and known chemical behavior. Atomic weight was not, in the modern sense, the final explanation of elemental order, but at that time it was one of the strongest guides chemists possessed. Mendeleev compared elements by weight, by the formulas of their oxides and hydrides, and by their broader chemical similarities. He was looking for a sequence in which recurring types of behavior would reappear at intervals rather than remain scattered randomly. That idea was not entirely new, since others had glimpsed partial periodicity before him, but Mendeleev carried it farther, more confidently, and with greater structural discipline. A widely repeated story describes him writing the known elements on separate cards and rearranging them until the right pattern emerged. While later retellings often dramatized this process, the central image is plausible because it fits the kind of comparison he was doing. The crucial point is not whether every detail of the anecdote survives strict historical scrutiny. What matters is that Mendeleev was actively manipulating chemical information, testing alignments, and searching for an arrangement in which atomic weight and chemical resemblance could be made to coexist. He was not simply reading a truth off the page. He was forcing the known facts to reveal whether they belonged to a deeper law. The arrangement he announced in the late 1860s was based on a striking principle. If the elements were ordered by increasing atomic weight, and a new row began whenever a certain family of properties returned, then similar elements tended to fall into vertical groupings. This was the birth of the periodic law in its early form. Chemical properties were not distributed randomly across the elements, but recurred in a regular way when the elements were arranged according to weight. The table was, in that sense, a map of recurrence. This achievement required judgment at every step. A purely mechanical ordering by weight would not have been enough because chemistry was not perfectly smooth. Some elements seemed to resist simple placement if one followed atomic weight rigidly without regard for chemical character. Mendeleev chose to trust chemical relationships more deeply than a blind numerical sequence. In some cases, he believed accepted atomic weights must be wrong if they disrupted an otherwise convincing family pattern. This was a remarkable decision. It meant he treated the table not as a passive summary of existing measurements, but as an active scientific argument about the structure of reality. When measurement and pattern came into tension, he did not automatically surrender the pattern. That confidence is one of the reasons his table became historically decisive. A weaker thinker might have produced a tidy arrangement of the known elements and stopped there. Mendeleev was doing something more demanding. He was asking whether the arrangement deserved to be trusted even where the evidence was incomplete or awkward. A true scientific law does not merely sort what is already known. It reveals where current knowledge is distorted, unfinished, or missing. This is why the gaps in Mendeleev's table mattered so much. He did not try to force every known element into a filled and seamless scheme. Instead, he left certain spaces empty where the logic of periodic recurrence demanded an element that had not yet been discovered or adequately characterized. That move was intellectually bold because it reversed the normal relationship between fact and classification. Rather than waiting for all the elements to be known before building a system, he used the system to declare that some elements must exist even though chemists had not yet isolated them. The table was no longer just an arrangement. It had become a predictive framework. The predictive power of the table came not from vague hope, but from the regularity Mendeleev believed he had found. If a missing element belonged beneath or beside certain known ones, then some of its properties could be estimated by comparison with its neighbors. Its atomic weight could be approximated. The nature of its oxide and chloride could be anticipated. Its density, physical character, and chemical behavior could be outlined in advance. In this way, the table turned absence into a scientific clue. A blank space was not ignorance alone. It was structured ignorance. Mendeleev's first published table in the late 1860s already contained the essential insight, but his later refinements made the system clearer and more forceful. In the early 1870s, he presented a more mature formulation in which the periodic law and its consequences were expressed with greater confidence. He predicted in detail the existence and properties of several then unknown elements, including the substances he referred to by provisional names, meaning one place beyond known members of a family. These predictions became famous not because prediction itself was unheard of in science, but because they were precise enough to be tested decisively. Another reason the table was borne so powerfully in Mendeleev's hands is that he was willing to live with imperfection without abandoning order. The table he created was not complete in the modern sense. It was built before the discovery of noble gases, before the explanation of periodicity by atomic number, and before the quantum description of electron structure. Even so, he recognized that an incomplete law can still be a real law if it captures something fundamental. He was seeing the architecture before the inner mechanics were known. This distinction is essential. Many scientific discoveries begin with pattern before explanation. The pattern must be trusted first, and only later does a deeper theory reveal why it exists. It is also important that Mendeleev was not working in a vacuum. Other chemists, including Lothar Meyer, were approaching similar territory. The intellectual conditions for periodicity had matured. But Mendeleev's achievement was distinctive in both style and consequence. He did not merely notice recurrence. He built a practical table around it, defended its logic, accepted gaps, corrected weights when necessary, and drew out specific predictions. That combination of pattern recognition and scientific audacity gave his version unusual authority. He did not just glimpse a law. He acted as though the law had earned the right to reorganize chemistry. The birth of the table, therefore, marks a shift in how chemists could think. Before it, the elements were known individually and in partial families. After it, they could be seen as members of a single ordered system. Chemistry gained a new kind of unity. It became possible to speak not only of oxygen or sodium or sulfur in isolation, but of the overall pattern into which such elements fit. This did not make chemical individuality disappear. Each element remained distinct, but their distinctness was now framed by recurrence rather than by isolation. The table also changed memory itself. A student of chemistry no longer had to treat elemental behavior as a purely separate set of facts. Knowledge could now be compressed into structure. Group relationships, valence patterns, and broad chemical tendencies could be understood as expressions of position within a system. This is one of the deepest powers of science. It reduces the burden of memorizing isolated truths by revealing the order that binds them. Mendeleev's table did this for chemistry with extraordinary force. When later discoveries confirmed the existence of elements that fit his reserved spaces, the table's status grew from plausible framework to profound law. But even before those confirmations, the conceptual birth had already happened. The decisive step was the realization that the elements formed a repeating arrangement, and that the arrangement could guide inquiry into the unknown. In that sense, the table was born the moment Mendeleev trusted periodicity enough to let it overrule the temptation of completeness. Modern science explains the periodic table differently. Today, the deeper foundation lies in atomic number and in the quantum structure of electrons around the nucleus. Similar chemical properties recur because electron configurations recur in patterned ways as nuclear charge increases. Mendeleev did not know this. Yet his achievement remains one of the clearest examples in science of a correct large-scale pattern found before its microscopic cause was understood. He discovered a law at the level of chemical behavior that later physics would illuminate more deeply. That is one reason the birth of the table still feels so elegant. It shows that the world can sometimes be read correctly before it is fully explained. The moment also carries a broader lesson about scientific vision. Mendeleev did not discover a new continent of matter. The elements were already there, interacting exactly as they always had. What changed was the human arrangement of thought. A table on paper altered the meaning of the chemical world because it revealed that the world had a structure which the mind could mirror. This is one of the quiet triumphs of science. The universe does not need our categories, yet sometimes our best categories begin to resemble its hidden order. So the birth of the table was both practical and profound. It began in the ordinary labor of comparing data, preparing instruction, and sorting known facts. But from that labor emerged a framework that allowed chemistry to predict what was missing, reinterpret what was measured, and unify what had seemed scattered. It turned the elements into a system and made system itself part of chemical truth. There is something humbling in that transformation. For long stretches of time, the order of matter existed without human names, without symbols, without rows and columns. Then, for a brief moment in 1 century, a human mind arranged pieces of knowledge until the pattern became visible. We live short lives among things far older than us, yet now and then, the mind manages to align with a structure that was waiting long before we arrived. In that quiet meeting between thought and reality, there is something both scientific and deeply existential. Chapter 5. The Gaps That Changed Science. One of the most extraordinary features of Mendeleev's periodic table was not the way it arranged the known elements, but the way it made room for the unknown. At first glance, an empty space on a scientific chart might seem like an admission of ignorance. In Mendeleev's hands, it became something far more powerful. A gap was not merely a place where knowledge had failed to arrive. It was a place where the logic of nature appeared to demand that something existed, even if chemists had not yet isolated it. This transformed the periodic table from a clever classification into a scientific instrument of prediction. To understand why this mattered so deeply, it helps to remember what most classifications do. Ordinarily, a classification gathers things already known and places them into categories after the fact. It is a way of organizing what has been observed. Mendeleev's table did more than that. Because he believed that the properties of the elements recurred in a lawful way when arranged by atomic weight, he concluded that the structure of the table itself could reveal what chemistry had not yet seen. If a vertical family of similar elements was interrupted, and if the surrounding pattern remained strong, then the interruption might not be a defect in the law. It might mean that an element was missing from the current inventory of science. This was a daring move. It meant that Mendeleev trusted the periodic pattern enough to resist the pressure of apparent completeness. Many systems can look neat if one forces every known object into place. Mendeleev chose a harder path. He left deliberate blanks where the regular recurrence of chemical properties seemed to require them. In doing so, he treated absence as evidence. That was a profound shift in scientific reasoning. The unknown was no longer a vague outside region beyond the boundary of knowledge. It had begun to acquire shape from within the system itself. Among the most famous of these predicted absences were the elements Mendeleev called Ica boron, Ica aluminium, and Ica silicon. The prefix he used came from Sanskrit and meant one beyond, indicating that each hypothetical element should appear beneath a known one in the table. These were not empty names chosen at random. They reflected positional reasoning. If a gap lay below boron or aluminium or silicon, then the missing element should resemble the known element above it in broad chemical character, while also differing from it in ways consistent with its place lower in the group. That meant the gap could be described before it was filled. What made Mendeleev's approach so convincing was that he did not stop at saying a missing element ought to exist. He went further and predicted many of its properties in advance. He estimated approximate atomic weight, expected density, oxide behavior, and other chemical traits by studying how neighboring and related elements behaved. This was a different kind of scientific confidence than mere speculation. He was not simply saying, perhaps nature contains something here. He was saying, if the periodic law is real, then the missing substance should behave in this broad way and should enter compounds of this approximate character. That is why later confirmations had such force. They did not merely add new substances to chemistry. They tested the table itself. The first of the famous confirmations came with gallium, discovered in the middle of the 1870s by the French chemist Paul-Émile Lecoq de Bois-Baudran. Gallium had been detected spectroscopically, and when its properties were studied, it soon became clear that it resembled Mendeleev's predicted Eka aluminium in striking ways. The match was not perfect in every early measurement, but it was close enough to attract serious attention. In fact, Mendeleev argued that one of the measured properties, the density, had likely been determined incorrectly because it did not fit the expected pattern. Later measurements showed that the corrected value moved closer to what Mendeleev had anticipated. This was a remarkable episode because it meant that the table was doing more than waiting to be confirmed by experiment. It was correcting experiment through theory-guided expectation. Gallium mattered because it showed that a reserved space in the table could correspond to a real substance in the world. The gap was not a decorative hole. It was a trace of an undiscovered reality. Mendeleev had not seen gallium in a flame or ore, but he had seen the structural need for something like it. This is one of the rare moments in the history of science when an orderly framework became so persuasive that it could reach ahead of direct observation and still land close to the truth. Not long after that came scandium, discovered in the late 1870s by Lars Fredrik Nilsson. This element corresponded closely to Mendeleev's Eka boron. Again, the importance was larger than the substance itself. Another gap had acquired a body. Another absence had turned into matter. Each such discovery made it harder for chemists to dismiss the periodic law as a coincidence or a convenient teaching device. The table had begun to demonstrate that it knew something about nature, not yet captured by the laboratories of the day. Then came germanium in the middle of the 1880s, discovered by Clemens Winkler. Its relation to Mendeleev's predicted Eka silicon proved especially important because the agreement between predicted and observed properties was impressively strong. By this stage, the pattern was difficult to deny. Gallium, scandium, and germanium were not random victories. They were the filling in of structured absences that had been publicly anticipated in advance. The predictive success of the table did not merely add prestige to Mendeleev's reputation. It changed the status of the periodic system within chemistry. What had once been a bold arrangement now looked increasingly like a law of nature. This is why the gaps changed science. They altered what chemists believed a classification could do. Before this, classifying the elements could seem like a matter of convenience, memory, or descriptive order. After the successful predictions, classification had become explanatory and generative. It could reveal not only what was already known, but also what had to be sought. The periodic table became a guide to discovery. That changed the psychology of chemistry. The field no longer faced the unknown as a shapeless region. It could search for missing members of a meaningful order. There is an important scientific subtlety here. Mendeleev's predictions were not magic, and they were not based on a modern understanding of atomic structure. He was still working with atomic weights rather than atomic numbers, and he did not know that the deeper basis of periodic recurrence lay in nuclear charge and electron arrangement. Yet the success of the gaps shows that a scientific pattern can be real even before its innermost cause is understood. Mendeleev had grasped the architecture of chemical repetition without possessing the full microscopic explanation. That is one of the reasons his accomplishment remains so admired. It demonstrates that lawful structure can be discovered at one level of science and explained only later at another. It is also worth noting that Mendeleev was not right about everything. Like most major scientists, he had missteps, resisted some later developments, and made predictions that were not all equally successful. But this does not weaken the historical importance of the famous gaps. In science, decisive success does not require universal perfection. What mattered was that the periodic law proved itself in the most demanding possible way, by predicting substances that were not yet part of accepted chemical reality. A theory that can survive such a test earns a different kind of authority. The gaps also changed the relationship between known and unknown matter. Before the periodic table, an undiscovered element was simply something not yet encountered. After Mendeleev, some undiscovered elements became expected members of a larger order. Their absence was temporary rather than mysterious. This did not mean every missing space would immediately be filled, or that all later discoveries would be simple. But it did mean that chemistry had acquired a map with contours extending beyond direct experience. A blank could carry information. An omission could become a research program. Later developments in chemistry and physics would deepen this story. The discovery of noble gases required the table to expand. The recognition that atomic number rather than atomic weight gives the most fundamental ordering principle refined the law. Quantum mechanics later explained why similarities recur across rows and groups. But none of that erased the significance of Mendeleev's empty spaces. On the contrary, those later developments made the original insight look even stronger. He had recognized an authentic regularity in matter before the internal machinery of that regularity was understood. The gaps had pointed toward a truth larger than the theory available at the time. This is part of what makes the episode so beautiful in the history of science. We often imagine knowledge as a gradual filling in, as though the world begins empty and science slowly paints it with facts. But Mendeleev's gaps suggest something more subtle. Sometimes the structure comes first, and the missing pieces are recognized because the pattern surrounding them is already visible. In such moments, ignorance is not a featureless darkness. It has edges. It has shape. It is illuminated by the order of what is known. So the gaps changed science because they proved that chemistry had crossed into a new kind of maturity. It was no longer only describing substances already in hand. It had begun to understand the relations among substances strongly enough to forecast what had not yet been found. The table became not just a ledger of matter, but an argument about the hidden coherence of nature. And when the missing elements appeared, they did not simply complete rows and columns. They confirmed that the world was more intelligible than it had once seemed. There is something quietly existential in that. A human mind, working with incomplete measurements and finite tools, looked at a scattered set of substances and trusted that the missing parts of reality would someday answer to the pattern already seen. For a brief creature in a vast universe, that is a remarkable act of confidence. The empty places were real before anyone could touch them, and the order that held them was already there, waiting for discovery with a patience far older than us. Chapter 6. Predicting the Unknown. What made Mendeleev's periodic system so scientifically powerful was not only that it left spaces for missing elements, but that it turned those spaces into structured expectations. A gap by itself is only an absence. In Mendeleev's hands, a gap became a provisional portrait of matter not yet found. He believed that if the elements were arranged in a natural order, then the place of an unknown element within that order should already constrain its behavior. Its approximate atomic weight, the kinds of compounds it would form, the character of its oxide, its density, and even something of its physical appearance could be inferred from the neighboring elements around it and from the vertical family to which it belonged. That was the deeper meaning of prediction in the periodic table. Mendeleev was not guessing wildly about hidden substances. He was reasoning from recurrence. The system itself, if genuine, should cast a shadow forward into the unknown. This style of reasoning was unusually strong for 19th century chemistry because the inner architecture of the atom was still unknown. Mendeleev had no access to protons, electron shells, or quantum mechanics. He could not explain periodicity in the way modern chemistry does. Yet he could still observe that when elements were placed in a consistent sequence, certain properties returned in patterned ways. Similar valences, similar oxide formulas, related chemical reactivities, and broad physical parallels seemed to recur at intervals. From that recurring structure, he inferred that an undiscovered element should not be treated as a mystery without features. It should be treated as a member of a family whose character was partly legible in advance. This is one of the remarkable things about science. Sometimes explanation arrives later than pattern recognition, but the pattern can still be trustworthy enough to guide discovery. Mendeleev's provisional names reveal how positional this reasoning was. He often used the prefix eka, meaning one beyond, to designate an element expected one row below a known element. Eka aluminium, Eka boron, and Eka silicon were not poetic inventions. They were placeholders rooted in the logic of the table. The unknown substance beneath aluminium should resemble aluminium in broad chemical type, while differing from it in ways expected of a heavier group member. The same applied to the predicted substances beneath boron and silicon. This method allowed Mendeleev to move beyond the statement that a missing element ought to exist. He could ask what sort of chemistry that element should display if the periodic law was real. Position became evidence. A location in the table was not an empty square on paper. It was a compressed statement about relationships. And relationships in chemistry often carry more predictive weight than isolated measurements. His predictions were built from several kinds of comparison at once. He considered atomic weight as one guide, since that was the principal numerical ordering available to him. He also paid close attention to valence patterns and to the formulas of oxides and chlorides formed by neighboring elements. He compared the density and metallic or non-metallic character of nearby substances, and he tried to infer how these tendencies should continue into the missing place. In effect, he was using a local field of evidence rather than relying on any single property alone. If an unknown element sat between or beneath known ones, then its character should be constrained by the trends running through that region of the table. This is why his method was more robust than mere analogy. He did not just say that an undiscovered element might resemble one familiar substance. He cross-checked several converging regularities at once. That made his forecasts unusually testable. The prediction of Ica aluminium, later identified with gallium, shows this method clearly. Mendeleev expected an element with an atomic weight near that of the open position below aluminium. He predicted that it would form an oxide analogous in broad form to the oxides of its neighbors, and that it would show a relatively low melting point and a density within a narrow range. When gallium was discovered by Lecoq du Bois-Baudran, its general chemistry fit the prediction strikingly well. Mendeleev even challenged one of the early measured density values because it did not suit the periodic expectation, and later work moved the accepted value closer to his forecast. This episode mattered not because every numerical detail was exact to modern standards, but because the underlying method had shown real power. The table had not merely welcomed a new element after discovery. It had anticipated the broad profile of that element before it was isolated. The case of Ica boron, later scandium, carried a similar lesson. Scandium occupies a place that in Mendeleev's framework required a light element with chemical behavior linked to that position in the system. When scandium was eventually isolated, its properties corresponded closely enough to the predicted role that the case strengthened confidence in periodic reasoning. This was important because successful prediction in science gains force when it works across more than one example. A single agreement can be dismissed as luck or loose interpretation. Repeated agreement across several independent cases suggests that the system is tracking something real in nature. With scandium, the table again showed that a blank was not merely a confession of missing data. It was a statement that the hidden member of a family should eventually reveal itself with broadly expected chemical habits. Perhaps the most celebrated example was Ica silicon, later germanium. Here the agreement between prediction and discovery was especially compelling. Mendeleev forecast an element of roughly the correct atomic weight, with a density close to the observed value, a gray appearance, and chemistry consistent with a position beneath silicon. When germanium was isolated by Clemens Winkler, it provided what many historians and chemists regard as one of the most persuasive vindications of the periodic system. The fit was not a vague resemblance. It was the kind of detailed correspondence that makes scientists trust a framework more deeply than before. In effect, the periodic table had reached into the future and returned with a substance that matched the shape of its own expectation. This is why germanium became such a famous episode in the history of chemistry. It showed that Mendeleev was not simply arranging facts elegantly. He was reading a lawful structure of matter strongly enough to forecast a real constituent of the world. There is a deeper methodological point here. Prediction in science is not all of one kind. Sometimes a theory predicts a number with exceptional precision. Sometimes it predicts a class of behavior or the existence of an object. Mendeleev's success lay in predicting a chemically meaningful profile. He could not derive his results from the microscopic theory that later scientists would possess, but he could state in advance what kind of element should appear and how it should behave relative to others. That is enough to count as a major predictive triumph. In fact, it is one of the clearest examples in science of a classification becoming explanatory. The table no longer served only to summarize known matter. It became a machine for generating disciplined expectations about matter not yet known. That altered the status of chemistry itself. A field once burdened by accumulation had become capable of structured foresight. At the same time, predicting the unknown did not mean that Mendeleev was infallible. Some of his further expectations were less successful, and later discoveries forced revisions in the table. Noble gases, isotopes, and the replacement of atomic weight by atomic number complicated the original picture. But this does not diminish the importance of what he achieved. Scientific insight is rarely perfect on first arrival. What matters is whether a pattern survives correction and grows stronger when the theory beneath it improves. That is exactly what happened with periodicity. 20th century atomic theory explained why Mendeleev's predictions worked as well as they did. Similar chemical properties recur because electron structures recur in patterned ways as nuclear charge increases. Mendeleev did not know that mechanism, yet he had already identified the large-scale architecture it produced. He saw the shape before anyone could see the machinery. This is one reason the history of prediction around the periodic table remains so philosophically rich. It shows that science does not always advance by moving from tiny causes outward to visible effects. Sometimes it moves the other way. A broad pattern in observable behavior becomes clear first, and only afterward is its deeper physical cause uncovered. Mendeleev's work belongs to that kind of discovery. He trusted a regularity in the visible chemistry of the elements strongly enough to let it speak about invisible possibilities. In doing so, he gave scientists a way to treat the unknown not as pure darkness, but as something partly illuminated by the order already present. The blank spaces of the table were transformed into predictions, because he believed that nature is not a random pile of substances. It is a system whose missing parts can, under the right conditions, be inferred from the coherence of the whole. That lesson extends beyond the history of chemistry. Human knowledge is always incomplete, and most of reality lies outside any one moment of understanding. Yet the success of Mendeleev's predictions suggests that ignorance is not always shapeless. When the known world is ordered well enough, even what has not yet been found may begin to show an outline. There is something quietly existential in that fact. We live inside only a fragment of the universe, but sometimes the fragment is structured enough to let us sense the whole more clearly. Mendeleev could not see the hidden elements directly, yet by trusting the order of matter he could speak about them before they entered human hands. In a finite life, that is a remarkable kind of contact with what lies beyond immediate experience. Chapter 7. When the Elements Were Found. A scientific prediction becomes truly consequential only when the world answers back. For Dmitri Mendeleev, that answer did not arrive all at once. It came in stages, through laboratories in different countries, through difficult measurements, and through the slow conversion of skepticism into respect. The periodic table had already offered a bold claim. The missing elements were not imaginary placeholders, but real substances whose properties could be anticipated from their position in a larger order. That claim remained vulnerable until the predicted substances were actually found. When they finally were, chemistry changed. The tables ceased to be merely persuasive. It became demonstrably powerful. The first major confirmation came with gallium. In the middle of the 1870s, the French chemist Paul-Émile Lecoq de Bois-Baudran was studying a zinc ore by spectroscopic methods. Spectroscopy had become one of the most important tools of 19th century chemistry because elements could be recognized by the distinct lines they produced in emitted light. Lecoq de Bois-Baudran detected a new violet spectral signature and soon isolated a previously unknown metallic substance from the ore. He named it gallium. By itself, this was already a real discovery, but what made it historically explosive was its relationship to Mendeleev's predicted Ica aluminium. Gallium appeared where the periodic system had suggested an undiscovered element should be, and its broad chemical behavior matched the expected type closely enough to draw immediate attention. This was not simply a matter of finding a new element somewhere in nature. Chemists had discovered new elements before. What was different here was that gallium arrived as if it had been awaited. The table had prepared a space for it in advance. Mendeleev had expected an element beneath aluminium, with an approximate atomic weight in the right region, a characteristic oxide, and a density and physical behavior consistent with that place in the system. Gallium's discovery therefore acted as a test of the table's internal logic. It was not enough that a new substance existed. It had to resemble the predicted kind of substance. That is what made the case so compelling. Gallium did not merely enlarge the inventory of chemistry. It behaved like an answer to a question that had already been asked. There was even a revealing dispute over measurement. One early reported density for gallium did not fit Mendeleev's expectation as well as the rest of the evidence did. Mendeleev argued that the measurement must be wrong because the overall pattern of properties pointed too strongly toward the predicted element for the mismatch to be ignored. Later work revised the density closer to what the periodic reasoning had implied. This was an extraordinary moment in the history of science. A table on paper was not passively receiving confirmation from experiment. It was exerting pressure on experiment, helping chemists decide which measurements to trust and which to re-examine. The theory-guided structure of the table was beginning to shape the interpretation of the data. Still, one success could always be dismissed as a lucky alignment. A single agreement, however striking, might be treated as coincidence, especially in a field as complex as chemistry. The deeper turning point came when additional predicted elements were found and placed into the expected pattern with similar force. In the late 1870s, the Swedish chemist Lars Fredrik Nilsson was analyzing rare minerals and isolated the oxide of a new element. This element was later recognized as scandium. Its significance extended well beyond national credit or laboratory skill. Scandium corresponded closely to Mendeleev's predicted Ica boron. Once again, the table's missing space was no longer empty. A second reserved place had turned into matter. Scandium's importance lies partly in repetition. In science, repeated success across separate cases is what converts a suggestive pattern into a serious law. The discovery of gallium had shown that one gap could be real. The discovery of scandium suggested that the method itself was real. The table was not simply fortunate in one instance. It was beginning to demonstrate a stable relation between chemical order and undiscovered substances. Each new confirmation made it harder for critics to argue that Mendeleev's system was a clever but temporary arrangement. The unknown was being found where the table said it should be found. Then, in the middle of the 1880s, came germanium, discovered by Clemens Winkler. Of the famous early confirmations, this one is often regarded as especially persuasive because the agreement between predicted and observed properties was so strong. Germanium matched the role of Mendeleev's ecosilicon with remarkable closeness. Its atomic weight, density, and chemistry aligned in ways that made the power of the periodic system difficult to deny. By this point, the narrative had become unmistakable. Gallium, scandium, and germanium were not isolated triumphs scattered by chance. They were the filling of structured absences that had been publicly anticipated. The table had not only survived experimental contact with the world, it had gained authority from it. What happened next was not merely an increase in Mendeleev's fame. The discoveries changed the standing of the periodic law within chemistry as a whole. Before these confirmations, the periodic system could still be viewed as one of several competing classifications. Some chemists admired it, some doubted it, and some treated it as useful but provisional. After the predicted elements were found, the balance shifted. The table had demonstrated that classification could do more than tidy knowledge. It could reveal hidden members of nature before direct observation caught up. That kind of success carries unusual epistemic force. A framework that predicts new realities earns a deeper kind of trust than one that only arranges known facts. It is also important to see how careful the confirmations really were. The discovered elements were not declared matches merely because they occupied the right approximate position. Their compounds, oxide behavior, and general chemical character had to be studied. The strength of the historical episode lies in this convergence. The fit was not symbolic, it was chemical. Gallium behaved like the missing element beneath aluminium. Scandium behaved like the missing element beneath boron. Germanium behaved like the missing element beneath silicon. The table's success was therefore not rhetorical alone. It was anchored in material properties measured in laboratories. That is why the discoveries persuaded working chemists, rather than merely inspiring public wonder. And yet the discoveries did not mean that the periodic table had reached its final form. Important developments still lay ahead. Noble gases had not yet been integrated into the system. The distinction between atomic weight and atomic number had not yet been settled in the modern sense. The inner reason periodicity works so well would only become clear in the 20th century with the rise of atomic physics and quantum mechanics. The table that was vindicated in these decades was therefore real but unfinished. This makes the episode even more impressive. The pattern was strong enough to guide discovery before the deeper microscopic basis of the pattern was known. Mendeleev and his contemporaries could see the architecture of recurrence long before they understood its full internal mechanism. There is a revealing asymmetry here. The elements themselves had always existed. Gallium did not begin to exist when Lecoq-du Bois-Baudran isolated it. Scandium did not come into being only when Nilsson separated it from mineral material. Germanium was not created by Winkler's recognition. These substances were present in the world long before they entered human science. What changed was not nature itself, but the relation between nature and human understanding. The table gave chemists a way to expect what had previously been invisible to them as members of a system. When the elements were found, the universe was not changing its structure. The human mind was catching up to it. This is why the episode holds such a special place in the history of science. Many discoveries reveal something hidden. Fewer reveal that what was hidden had already been mapped in outline by theory. The periodic table did that. It turned undiscovered substances into anticipated realities. When those realities emerged from ores and spectral lines, they seemed less like surprises than like arrivals. The world had been holding them all along, and chemistry had finally learned how to wait for them in the right places. The emotional effect on the scientific community should not be underestimated. Science depends on discipline, evidence, and criticism, but it is also sustained by moments when reality answers a human pattern with unexpected generosity. The discovery of the predicted elements gave chemists a rare experience of intellectual vindication. It suggested that the order they had begun to glimpse among the elements was not a projection of the mind alone. It was something written into matter itself. That feeling can reshape a discipline. Once chemists saw that the table could successfully call hidden substances into view, it became much harder to think of the elements as a random collection. Periodicity began to feel less like an organizing convenience and more like a deep truth about the structure of chemical existence. From a modern perspective, these discoveries also remind us that scientific confirmation is rarely a single event. It is a sequence of encounters between expectation and evidence. Gallium opened the door. Scandium widened it. Germanium made the pattern difficult to dispute. Each element strengthened the bridge between theory and world. That bridge was not perfect, and later science would rebuild parts of it with stronger materials, especially through atomic number and quantum theory. But the essential crossing had already occurred. The table had predicted the unknown, and the unknown had appeared. There is something quietly existential in that moment. The substances were real before anyone named them, before anyone purified them, before anyone saw their spectral lines. Human life is brief, and our knowledge is always partial. Yet now and then the mind discovers an order strong enough to reach beyond what it has already touched. When the missing elements were found, chemistry learned that reality could answer to a pattern glimpsed in advance. And perhaps that is one of the most calming truths in science. The world does not become orderly when we understand it. It has been orderly all along. Chapter 8. Why the periodic table really works. The periodic table works because the elements are not arranged by superficial resemblance or by historical accident. They are arranged by a physical property built into every atom, the number of positive charges in the nucleus, which is the atomic number. In modern chemistry, that number is understood as the count of protons in the nucleus, and it determines the identity of the element itself. If an atom has 1 proton, it is hydrogen. If it has 6, it is carbon. If it has 26, it is iron. This is the deeper foundation that later science added to Mendeleev's earlier insight. He had arranged the elements mainly by atomic weight and chemical behavior, which worked remarkably well, but the true organizing principle turned out to be nuclear charge. Once that was understood, the periodic table was no longer just a successful pattern. It became a map rooted in atomic structure. That shift matters because atomic weight is not always the most reliable guide to elemental order. Different elements can have atomic weights that do not increase in a perfectly smooth way, especially once isotopes are taken into account. Isotopes are atoms of the same element that have the same number of protons, but different numbers of neutrons. Because chemistry depends primarily on the electron structure set by nuclear charge, not on the exact mass of the nucleus, atomic number gives the more fundamental sequence. This is why the modern periodic law states that the properties of the elements recur periodically when the elements are arranged in order of increasing atomic number. The table works, in other words, because the buildup of positive charge in the nucleus organizes the electrons around it in repeating patterns, and those electron patterns govern chemical behavior. The key to the whole story lies in the electrons. Chemistry happens mostly through the outer electrons of atoms, the ones farthest from the nucleus and most available for bonding, transfer, and sharing. Atoms do not place these electrons randomly. Quantum physics allows electrons only certain kinds of allowed states, often described through shells, subshells, and orbitals. The lowest energy arrangements are filled first, and as the number of electrons increases from one element to the next, these allowed states fill in an ordered sequence. Because the sequence of filling has a repeating large-scale structure, the outermost electron arrangements also repeat in recognizable ways. When outer arrangements recur, broad chemical properties recur with them. That is the deep reason the periodic table is periodic at all. This is why elements in the same vertical group often behave similarly even when they are otherwise very different in mass, size, or density. Lithium, sodium, and potassium, for example, all sit in the same group because each has one outermost electron in a comparable pattern. That shared outer structure makes them chemically related. They are all reactive metals, all tend to form ions with a similar charge, and all show family resemblances in the compounds they make. The halogens show a similar logic. Fluorine, chlorine, bromine, and iodine differ greatly in size and physical appearance, yet they behave as a recognizable family because their outer electron structures follow the same basic pattern. The periodic table works because it groups together atoms whose chemically active outer regions are organized in comparable ways. Periods, the horizontal rows, reflect a different part of the same story. As atomic number increases, electrons are added step by step into allowed states of increasing complexity. A new period begins when a new outer shell starts to fill. Across a period, the number of outer electrons changes in a regular progression, and that progression drives the changing character of the elements from left to right. Metals dominate the left side of many periods because atoms there more readily lose outer electrons. Toward the right side, atoms hold their outer electrons more strongly and often tend to gain or share electrons instead. By the time a filled outer shell is reached, a noble gas appears, and its chemical stability reflects the relative completeness of that outer electron arrangement. Then the pattern begins again on a new level. The table works because this stepwise filling of allowed electron states creates a rhythm in chemical possibility. The elegance of this explanation became clearer only after the rise of atomic theory in the 20th century. Niels Bohr's early quantum model helped show that electrons occupy discrete energy levels rather than arbitrary classical orbits. Later quantum mechanics replaced the older picture with a more complete account based on wave behavior, probability, and permitted quantum states. The details became more subtle, but the broad result remained. Electrons can inhabit only certain structured arrangements, and those arrangements repeat in patterned ways as nuclear charge increases. In that sense, the periodic table is a visible summary of quantum rules. What had first appeared as a chemical classification turned out to be a large-scale expression of the quantized architecture of the atom. This also explains why Mendeleev's table could work so well before anyone knew the full reason behind it. Chemical properties were already reflecting electron structure, even though electrons themselves had not yet been discovered when he proposed his periodic law. The recurring valences, oxide forms, and reactivity patterns he noticed were real manifestations of underlying atomic organization. He could see the regularities in behavior without yet knowing their microscopic source. Modern physics did not replace the periodic table so much as explain why it had been so successful. The later discovery of atomic number and quantum structure revealed that Mendeleev had found a genuine order of nature, not a convenient pattern imposed from outside. The table also works because the periodic recurrence is strong enough to support prediction, but not so rigid that it erases complexity. Not every property changes in a perfectly smooth way. Atomic size, ionization energy, electron affinity, metallic character, and bonding tendencies follow broad trends, yet they also show local irregularities. Some of these arise because subshell energies overlap. Some arise because half-filled or fully filled arrangements can be especially stable. Some appear more strongly in transition elements, where inner subshells complicate the simple patterns seen in the main groups. The table works not because nature is mechanically uniform, but because the irregularities themselves occur within a deeper structured framework. Chemistry remains rich and varied precisely because the recurring order is real without being simplistic. Transition elements are a good example of this richness. In these regions of the table, electrons are being added to inner subshells while outer electrons still influence chemistry. That produces more varied oxidation states and more complicated bonding behavior than in many main group elements. Even here, however, the periodic table still works because the possible electron arrangements are not random. They reflect quantum structure, energy ordering, and recurring patterns in how orbitals fill. The complexity is real, but it is organized complexity. The table is therefore not a rigid codebook so much as a compact map of structured possibilities. Another reason the table works so powerfully is that it connects microscopic structure to macroscopic experience. From the position of an element in the table, chemists can infer a great deal about its likely bonding, its common ionic forms, its reactivity, and the sorts of compounds it tends to make. This is why the periodic table became such a central tool in chemistry education and research. It is not merely a historical artifact. It is a compression of an enormous amount of physical knowledge. Once one understands that groups reflect shared outer electron patterns and periods reflect the progressive filling of allowed quantum states, the table becomes intelligible rather than merely memorable. There is also a deeper philosophical beauty in how the explanation unfolds. The periodic table appears at first as a chart of substances, then it becomes a chart of atoms. Then, more deeply still, it becomes a chart of quantized electron structures shaped by nuclear charge. Each level explains the one above it without destroying it. The familiar chemical world of reactivity, salts, gases, metals, crystals, and acids, turns out to rest on mathematical restrictions governing what electrons are allowed to do. The table works because matter is not built from arbitrary pieces. It is built from atoms whose internal architecture follows repeatable physical rules. And yet the periodic table is not the final layer of reality either. Beneath atomic number lies the nucleus, and beneath the nucleus lie protons and neutrons, and beneath them lie quarks and the interactions described by modern physics. The table remains a chemistry table, not a complete theory of existence. But that is part of its strength. It captures exactly the level at which the structure of atoms becomes the behavior of matter. It is where quantum rules become substances, reactions, and the material world of ordinary experience. That is why it remains one of the most successful summaries in all of science. So the periodic table really works because atoms are built in a lawful way. Electrons occupy structured quantum states. Outer electron patterns recur as nuclear charge increases, and chemical behavior follows from those recurring outer arrangements. Mendeleev first saw the repeating order from the side of chemistry. Later science revealed that the order reaches down into the architecture of the atom itself. What looks like a table of colored boxes is, in truth, a quiet record of how matter organizes itself. There is something quietly existential in that realization. The substances around us can seem ordinary, even dull, until one remembers that their behavior comes from deep rules written into the structure of atoms long before life existed to notice them. For a brief conscious being to look at a chart and discover that it mirrors the hidden order of matter is a strange privilege. The table works because reality was structured before we arrived, and because, for a little while, the human mind can learn to read it. Chapter 9. Mendeleev's Legacy in Modern Science. Mendeleev's legacy in modern science is far larger than the historical moment in which he arranged the elements into a convincing pattern. His deeper achievement was to establish the periodic system as a way of thinking about matter, a way that still shapes chemistry, physics, material science, education, and even the continuing discovery of new elements. The table associated with his name has changed since his lifetime. It is now ordered by atomic number, rather than atomic weight. It includes noble gases that were unknown to him when he first proposed his system, and it has been extended through synthetic elements created in modern laboratories. Yet the essential insight remains continuous with his work. The elements are not a random list, but members of a lawful order whose structure reveals real relationships in nature. That continuity is why Mendeleev still belongs to modern science rather than merely to its past. One part of that legacy lives in chemistry itself, where the periodic table became the central framework for understanding elemental behavior. Modern chemists do not consult the table merely as a memory aid. They use it because position within the table still gives meaningful information about electron structure, bonding tendencies, common oxidation behavior, metallic or non-metallic character, and broad reactivity. A chemist trying to understand why sodium behaves differently from magnesium, or why chlorine resembles bromine more than oxygen, is still relying on the periodic logic that Mendeleev helped establish. Later atomic theory explained why the table works so well, but it did not replace the table. Instead, it revealed that Mendeleev had discovered a real level of order in matter, one strong enough that modern chemistry still uses it as a working map. His influence also extends into the way chemistry is taught. Before a student can master organic chemistry, biochemistry, material science, inorganic chemistry, or chemical engineering, the student usually learns to read the periodic table as a map of patterns rather than a wall of facts. This is a profound educational legacy. Mendeleev helped turn chemistry from a subject that could feel like an endless catalog into one that could be organized through recurrence and relationship. Modern education still depends on that transformation. The table allows beginners to see that elements in the same group often behave in related ways, that changes across periods are not arbitrary, and that chemical properties can often be anticipated from structure, rather than memorized one by one. This way of learning reflects Mendeleev's deeper gift. He made the science of matter more intelligible. Another part of his legacy appears in the modern understanding of atomic structure. Mendeleev did not know about protons, electron shells, or quantum mechanics, yet his table guided science toward questions that later physics would answer. When Henry Moseley showed that atomic number, measured through X-ray relationships, provided the more fundamental ordering principle for the elements, he did not destroy the periodic system. He clarified it. The table became even stronger because its underlying basis was now tied to nuclear charge rather than approximate atomic weight. Quantum theory later explained why chemical properties recur across the table, showing that periodicity arises from the structured filling of allowed electron states. In this sense, Mendeleev's legacy reaches directly into physics. His system became one of the bridges by which 19th century chemistry was joined to 20th century atomic science. His importance in modern materials science is equally real, even if it is sometimes less visible. New materials are often understood and designed by thinking in periodic terms. The properties of semiconductors, catalysts, superconducting compounds, corrosion-resistant alloys, battery materials, magnetic materials, and advanced ceramics depend strongly on which elements are chosen and how their electronic structures interact. The periodic table does not solve these problems by itself, but it remains one of the first and most powerful guides in thinking about them. Silicon and germanium occupy particular roles in electronics because of their position and electron structure. Transition metals behave as they do in catalysis and alloy formation because of their partially filled subshells and recurring periodic behavior. Even highly specialized research into functional materials often begins, quietly, with periodic reasoning. This too is part of Mendeleev's legacy. He gave later science a framework that still helps connect atomic identity to practical matter. There is also a modern legacy in the discovery and naming of elements themselves. Mendeleev's table did not end with the naturally common elements familiar in everyday life. Modern nuclear science extended the periodic table beyond uranium through the synthesis of transuranium and superheavy elements. These substances do not arise as stable materials around us in the ordinary way. Many must be created in laboratories through carefully designed nuclear reactions and may exist only briefly before decaying. Yet when scientists search for them, confirm them, and decide where they belong, they are still working inside the conceptual world Mendeleev helped define. The table remains open at its frontier. The continued recognition of new elements and the maintenance of the official table by international bodies show that periodicity is not only a historical success, but an active framework of modern research. This modern frontier also reveals something subtle about his legacy. The periodic table has endured not because every part of Mendeleev's original formulation was final, but because the central architecture was robust enough to survive correction. Noble gases were added. Atomic number replaced atomic weight as the most fundamental sequence. Isotopes complicated the older picture of atomic mass. Relativistic effects became important for the heaviest elements. Yet the table did not collapse under these refinements. It adapted, and in adapting it showed that Mendeleev had found not a temporary classification, but a lasting principle. This is one mark of a great scientific legacy. Later generations can improve the framework without abandoning its core truth. His legacy also lives in scientific standardization. Modern chemistry depends on a common language of names, symbols, atomic data, and measurement standards that allow scientists across the world to work coherently. Mendeleev himself cared about weights, measures, and practical scientific order in the Russian Empire. And in modern science, that impulse has become internationalized through organizations such as IUPAC. IUPAC now serves as the global authority for naming new elements, standardizing symbols, and maintaining critically evaluated chemical language and data. This may seem different from Mendeleev's table at first, but it is deeply related. The periodic system is not only an arrangement of substances. It is part of a broader culture of scientific order, one in which classification, naming, and measurement allow knowledge to become cumulative and shared. Mendeleev's legacy therefore survives not just in the visual form of the table, but in the very idea that chemistry should speak a precise universal language. There is a broader intellectual legacy as well. Mendeleev showed that classification in science can be more than bookkeeping. A truly successful classification can expose hidden relationships, guide future discovery, and reveal that what appears chaotic is governed by law. That lesson extends beyond chemistry. It resembles what later sciences achieved in other fields when they found ways to organize complex diversity into intelligible frameworks. The periodic system became one of the clearest examples of a scientific representation that is both simple to look at and profound in what it captures. It demonstrated that a diagram can be more than an illustration. It can become a condensed theory of reality. That is why thinkers continue to discuss Mendeleev not only as a chemist, but as an architect of scientific understanding. And yet perhaps the quietest part of his legacy is that he changed what it means to know matter. Before the periodic system, the elements could be experienced as a scattered multitude. After it, they could be understood as related positions in a wider order. Modern science has gone far beyond Mendeleev in detail, but it still inhabits that change in perspective. Whether one is studying the chemistry of a living cell, the composition of a distant star, the design of a new catalyst, or the fleeting existence of a superheavy nucleus, the periodic system remains present as a background grammar of matter. Its influence is so deep that it can become invisible, like any framework that has been fully absorbed into thought. But invisibility is not the same as irrelevance. It is often the sign of a scientific idea that has become foundational. So Mendeleev's legacy in modern science is not merely that he made an early periodic table. It is that he helped reveal a lawful structure in the elements that later chemistry and physics could deepen, refine, and continue to use. His insight survives in classrooms, laboratories, industrial materials, nuclear research, international standards, and the ongoing expansion of the table itself. Very few scientists leave behind a framework that remains both familiar and scientifically alive across so many generations. Mendeleev did. The table changed shape, but the order he recognized continued to hold. There is something quietly existential in that endurance. A human life, however brilliant, passes quickly, yet a true pattern in nature can outlast the person who first recognized it by centuries. Mendeleev is gone, but the order he helped reveal continues to guide minds that will never meet him. In that way, his legacy is not only scientific. It is a reminder that a brief human intelligence can sometimes touch something in the structure of reality that remains long after the hand that wrote it has fallen still. Chapter 10. The Quiet Beauty of Hidden Order. There is a reason the periodic table feels larger than chemistry. On one level, it is a practical scientific tool, an organized arrangement of the chemical elements in order of increasing atomic number, showing a recurrence of properties across rows and down columns. But on another level, it is something more unusual, a visible sign that nature contains deep regularities beneath apparent variety. Hydrogen and gold, oxygen and uranium, neon and iron do not look like members of one simple family when encountered in the world. They appear in stars, rocks, blood, air, oceans, machines, and living cells under wildly different conditions. Yet the periodic table reveals that these substances belong to a single ordered system. It does not erase their differences. It shows that their differences are structured. That is the quiet beauty at the heart of the table. It turns the diversity of matter into an intelligible pattern without making the world feel smaller. This beauty becomes clearer when one remembers that the table was not handed down fully explained. The periodic law was first recognized through chemical patterns, long before the internal structure of atoms was known in modern detail. Mendeleev and others could see recurrence in elemental behavior before science understood the deeper role of atomic number, nuclear charge, and electron arrangement. Later work showed that the table works because chemical properties recur when electrons fill way, allowed quantum states in repeating ways as the number of protons increases from one element to the next. What began as a chemical ordering became, in time, a window into atomic structure itself. That history matters because it shows two different kinds of beauty at once: the beauty of pattern first seen from the outside and the beauty of explanation discovered later within. There is also something striking about the way the periodic table compresses knowledge. It is only a finite arrangement of positions, yet each position carries a great deal of information. From the place of an element in the table, a chemist can infer broad features of its behavior, its likely bonding tendencies, and its relations to neighboring elements. This is one of the marks of a mature scientific idea. It does not merely name facts. It gathers them into a structure that reduces the burden of memory by revealing order. The table does not make chemistry simple in a trivial sense, because chemical reality remains full of nuance, exceptions, and rich detail. But it does make chemistry legible. It shows that beneath the overwhelming number of substances and compounds, there is a framework that allows the mind to move with confidence. Hidden order becomes usable knowledge. That intelligibility is part of why the periodic table has become one of the great icons of science. Few scientific images are recognized so widely. Even outside laboratories and classrooms, the grid of elements has become a cultural symbol of order, classification, and rational understanding. Yet, unlike many symbols, this one earned its status honestly. It is not famous merely because it is easy to print on posters or classroom walls. It is famous because it reflects a real architecture in matter. The groups and periods are not decorative categories invented for convenience. They arise from recurring physical relations among atoms. A chart became iconic because the world turned out to be chartable at that level. There's something deeply satisfying in that. A human-made image acquired power because it mirrors something that was already there. The beauty of hidden order is also visible in the table's flexibility. Over time, the table was refined, expanded, and reinterpreted. Atomic number replaced atomic weight as the most fundamental ordering principle. Noble gases found their natural place. New synthetic elements extended the known landscape of matter. Modern international bodies such as IUPAC continue to maintain the table, standardize its data, and adjudicate the naming and recognition of newly confirmed elements. This ongoing work is important because it shows that order in science is not the same as rigidity. A good scientific structure is stable enough to guide discovery and flexible enough to absorb correction. The periodic table has endured not because it was frozen in its earliest form, but because later science kept revealing that its underlying principle was sound enough to support growth. Even its incompleteness at the frontiers adds to its meaning. The known table extends through the currently recognized elements, including super-heavy ones produced only in specialized experiments and surviving for extremely short times. These edge regions remind us that the periodic table is not only a monument to past discovery, it is still an active boundary between what has been securely established and what remains uncertain. Scientists continue to investigate how far the table can be extended, how new nuclei behave, and how chemical identity itself should be understood at the most unstable extremes. So the table is both settled and unfinished. That combination is rare and beautiful. It means the pattern is real enough to trust but not exhausted. The order of matter still opens outward. The quietness of the table's beauty comes partly from the fact that it does not announce itself dramatically in daily life. Most people encounter matter through textures, colors, smells, tools, food, weather, buildings, blood, and breath. The world arrives as experience, not as atomic number. Yet the periodic table tells us that this ordinary world is grounded in a deep and orderly arrangement. The oxygen moved in by a breath, the calcium in bone, the sodium in nerve signaling, the iron in hemoglobin, the silicon in minerals and electronics, and the carbon in every living structure all belong to one connected framework. Chemistry does not reduce the richness of lived experience to a sterile chart. It reveals that the ordinary world is made possible by lawful relations so stable that life can build upon them. In that sense, the table is not separate from the human story. It is one of the reasons there can be a human story at all. There's also a philosophical gentleness in the periodic table because it offers order without pretending to explain everything. It does not answer every question about why the universe exists, why its laws take the form they do, or why matter is possible in the first place. It does not dissolve the mysteries of consciousness, time, or cosmic origin. What it does is narrower, and perhaps because of that, more trustworthy. It says that at the level of the elements, there is a lawful recurrence in nature, and that this recurrence can be studied, used, extended, and understood more deeply over time. Science is often strongest when it knows the scale at which it is speaking. The periodic table is a magnificent example of that kind of strength. It does not claim to be the whole truth. It shows a true part of reality with extraordinary clarity. This makes the table a rare bridge between humility and confidence. It invites confidence because its patterns are real, testable, and immensely fruitful. But it also invites humility because the order it displays was not created by human thought. It was discovered. The protons in nuclei, the allowed electronic structures of atoms, and the recurring chemical behaviors of matter were all in place long before any human arranged symbols into rows and columns. Scientific understanding, at its best, does not impose structure on a chaotic world. It learns to notice the structure that the world already contains. That is why the table can feel calm rather than triumphant. It is not a monument to human domination over nature. It is a record of human alignment with nature. And perhaps this is the deepest reason the periodic table continues to move people beyond the boundaries of chemistry itself. It offers a rare reassurance that the universe is not made only of isolated facts. Beneath the countless differences that fill the material world, there are repeating forms, lawful transitions, and relationships that can be known. For a mind living briefly inside a vast and often bewildering cosmos, that matters. It means that understanding is not always an illusion produced by convenience. Sometimes the world is genuinely ordered in ways the mind can meet. The table does not remove mystery, but it proves that mystery and intelligibility can coexist. The unknown remains, yet part of the unknown has shape. So the quiet beauty of hidden order is not just the beauty of one chart in one science. It is the beauty of discovering that matter itself carries rhythm. It is the beauty of realizing that the same universe that produces stars, minerals, oceans, machines, and living cells also permits a simple visual structure to summarize the deep relations among its elemental building blocks. And it is the beauty of seeing that what first looked like a scattered inventory of substances was, all along, a system waiting to be recognized. The table endures because it lets us witness something rare and steady, the meeting point between the order of nature and the patience of thought. In the end, that may be why the periodic table feels so calming. It reminds us that reality can be more coherent than it first appears, and that understanding sometimes comes not from forcing the world into shape, but from learning how to see the shape that was always there. We pass through the universe for only a moment, but for that moment, the mind can still recognize a pattern written into matter itself. That recognition does not make us large. It makes the world feel quietly knowable, and that is its own kind of peace. And that, my friend, is the quiet story of how one mind helped reveal the order hidden inside the elements. If you're still awake, there's another sleep science journey waiting for you on this channel. And if sleep is already close, then let go of the day, rest gently, and sweet dreams among the stars.